electrons to stop flowing. A resistor reacts with the field and converts a fixed amount of the electromagnetic field into kinetic energy. So it consumes some of the field, so that on one side of the resistor, there's a certain field volume, and on the other side of the resistor, that field volume has been reduced because it's been converted into heat. That isn't taught, but that's the reality of our world. So learn about fields. It will be very powerful in your career.
We are back with yet another episode, and today's episode is going to be intriguing and very enlightening as we have Daniel Beeker with us. Daniel has got 40 years of experience in electronic system. He is a technical director at NXP Semiconductors. Currently provides application support to NXP. Daniel has also served as a senior member of technical staff at FREESCALE Semiconductor. I would encourage the audience here to check out the link in the description to register for a free webinar on the topic, The $1 Billion Mistake, which is conducted by Daniel Beeker himself. So greeting Daniel, welcome to VLSI For All. We are honored to have you today with us.
Well, I want to just quickly say that I'm very honored that to be able to participate in your activities, and the opportunity to provide some mentoring is always welcome, especially at this point in my career. That's really what my goal is, to try to take my knowledge and expertise and experience and share it as much as I possibly can to help improve the overall experience and competency that's within the engineering community worldwide. So I've been in electronics since my first efforts in the Air Force. I was a radar technician and worked on tube radios and radar systems, and learned how to use an oscilloscope and a voltmeter and a tube tester. And also, one of the most interesting things was I was certified by a NASA soldering program. So I became quite proficient at soldering various types of components, and especially in these older systems, there were a lot of transformers, some of them with as many as 100 taps. And to replace a wiring harness on one of those was quite a challenge, and they always made me do it. So it was interesting. They would, in the training class, they would inspect the solder joints with a microscope, and if you didn't do it perfectly, you would have to do 10 more in order to make the systems go. And after that, I started working at Motorola Microsystems, and that was in 1980 as a technician in their microprocessor development tools group. And so I was working on 6,800 microprocessors back in those days. And from there, I worked my way into several engineering assistant positions, and eventually was offered the chance to move to Detroit with the automotive sales support team as a field applications engineer. And then I've been working in that role for the last quite a few years. Motorola at that time I was part of semiconductor product sector. That was spun off as FREESCALE Semiconductor. So we changed our name, but the job stayed the same. And about that same time, NXP was spun off from Philips, because they were the Philips semiconductor arm. And then a few years ago, NXP purchased FREESCALE, and we merged to form a larger, stronger company. And again, I'm still in the same role, supporting automotive customers. So my roles early in Motorola was working with development tools, and that moved into some of the other activities that I provided in the field as an applications engineer, where I supported microprocessors and microcontrollers and have been ever since. So
Yeah, that's great. I'm personally interested in knowing your journey in brief, but let's start with this first question for you. So Daniel, you support NXP customers with special function, development tools, and instrumentations. What's actually meant by special function, and also can you please talk about instrumentation support that you provide?
yeah, so this is one of the fun parts of my job. Because of my experience working with the instrumentation group at Motorola, the in-circuit emulators and evaluation boards, I was part of the 68020 in-circuit emulator design team and some of the other later ones. When I moved to the field, I found that there was first a need for more development tools because they were in short supply and the ones in the office were broken. So having been a former technician, the first thing I did was fix all the broken tools. And then I found that there were missing pieces of the puzzle. Maybe there was a connector that wasn't quite what was needed. And from there, I started doing, at the time, you could wire wrap things because the chips have pins on them. So I could build special adapters or demonstration products with simple wire wrap and solder and through hole components. And then as the parts evolved into surface mount devices, then I found I had to start getting involved with circuit board design, and I was working with third parties to support me in those functions and building more missing pieces in the tool chain. If somebody provided it commercially, then there was a solution. But if there wasn't a solution that was obstructing my customer's ability to create his product, then I would do what I needed to start building that. And that evolved into a need for special tools for a specific purpose. So I started working on pre-silicon emulation tools where we would take the IP that would be driven into the silicon compiler, program that into a gate array, hook it up with the IO structures that would eventually be in an in-circuit, in an IC, and create an in-circuit emulator for a device that didn't exist, and allow a customer to start developing their hardware and software months or even years before the silicon was available. And the first system I did was for a Ford program, and the design team was in Chennai. So my first trip to India was delivering the in-circuit emulator to support that device. And then as a result of that effort, we actually discovered a couple of issues, first with the customer's expectations and requirements for the behavior of the device. And we found some issues with our code, and we were able to make all those corrections way before tape out. So we saved at least one, probably two spins of silicon. And the result was a very happy customer. And Motorola discovered that they could charge a customer for that. And those were the first sales for my special tools. And from that, it has evolved into, through the NXP marketing system, I have over 500 products that I've developed over the years that we sell to customers. And so I actually have my own P&L and do about $3 to $4 million in revenue through my tools efforts, as well as my normal job as a field applications engineer. So it's become something quite interesting. The fun part is that when I look at a problem that a customer is facing and there's something missing, I will build a tool that I would want if I was going to be doing the design. And a lot of the times I anticipate that. So when a customer asks for something, do you have this type of interface? I can gladly say, oh, yes, I have one now. I did it last year for you. And that's very fulfilling. And the whole idea is to be able to remove every roadblock possible from the development process so that my customers can focus on developing their product rather than facing issues with the development environment itself. And that ends up with a much higher quality product for our customers and a shorter design cycle time. And then out of that also, my products that I sell have to be compliant for at least consumer. And early in my career as a field engineer, I found that there was a lot of problems with EMC. And I would work with the customers, and I really didn't understand it at the time. And we would sit next to the chamber and we make small changes to the board and retest it again and pray that it would work without an idea of what really was going on. And we even hired outside consultants a couple of times to provide solutions, and they were not any more experts on it than I was. And they would come up with these incredible requests for changes in the circuit board and the circuit, adding, $5, $10, $20 of cost with the band-aids that they put on there. And then there was still no guarantee that it would work. So from that, I had to become conversant in good design techniques. And that's another story in itself, where I was working on another pre-silicon emulator, and my service bureau was doing the circuit board design. And there was something we used called the Motorola Active Probe Interface. And that was the standard. MAPI standard was it for board-to-board connections. And I was using that because that was the standard emulator interface that we had used for all the products that I worked on in the factory. And my designer said, you don't want to do that. It doesn't do the things you think it does. And this was specifically about the separate analog and digital grounding schemes for the connectors. And I go, what do you mean? This is the Motorola standard. We've done this for years. You worked for me. You really need to use this approach for the connector interface. And he's going, no, you really don't want to do this. He said, this is not what you want. And I started to get upset because, he's doing a design for me, and I wanted it my way. And he said, you need more training. And I'm going, I don't need training. I've got 20 years of experience doing high-end emulator designs. He says, no, you need to go to training, and it's in California. Well, my response to that was, I need to go to training, and it's in California. And I told my managers, I need to get some training, and it's in California. And he approved the training. And I went to my first class at PCB West. It was a 2-day signal integrity class with Rick Hartley. And 5 minutes into Rick's class, I knew that every design I ever did worked by accident, not by design. And I tell you what, as a senior engineer, to find out that you really didn't know what you were doing was one of the most humbling experiences I ever had. So my immediate response was to start pounding Rick with questions. And finally, at the end of the first couple of hours, we had a break, and he's going, who are you and why are you in my class? And I said, I'm Dan Beeker from Motorola, and I really need to know this stuff. And since then, we've become great friends. And it started my journey where through a couple of other very fortunate events, I met Ralph Morrison and was able to hire him as a trainer for one of the FREESCALE technology forums. And at the class that he taught, it was very apparent that his approach was absolutely correct, and nobody else seemed to know what they were talking about. And from that, we became friends. He decided I was going to be his apprentice, and he was going to teach me field physics or kill me trying. And so he is very patient mentoring of me and putting up with my cluelessness, because I really didn't want to believe in fields. I was this digital circuit guy. It's ones and zeros. You hook the wires up, it works. And my experience was all in, TTL, things where the transistors were still extremely large and switching very slowly compared to what we have today. And all the guidelines that I used were developed based on those technologies. And it really wasn't even done where the guidelines were what worked. They were guidelines which presented what didn't cause it to seem to fail. So even in those days, you could do a lot of very bad things and it wouldn't make the design fail. Doing those things today is one of the most terrible tragedies of our industry. Is the result is that most designs are going to fail EMC. And that's been my mission, especially since Mr. Morrison passed away. One of the greatest victories in my career was I did a training class for the applications and design community at FREESCALE in Austin. So these were the chip guys and the evaluation board guys. And Ralph was in the audience. And after I gave my talk, he walked up to me, and I was afraid he was going to yell at me because I said something wrong. And he said, "Dan, I think you finally have it." And that has given me the confidence to move forward using his science-based approach to design. And as a result, the designs that I do are always compliant first time. And when I work with my customers and with the NXP design community, we have success first time. So that's the beauty of the science-based approach. And that's what I try to push every single day to my customers, to my peers, and every chance I get, which is why this is so exciting for me to speak with you today.
Cool, cool. That was great, really great. So Daniel, throughout your experience and throughout your journey, other than technical skills, what other life skills do you think would have helped you in grabbing opportunities, or maybe just climbing this hierarchy of in the getting promotion or something like that? Was it communication skill or something that like leadership skill or something like that?
Certainly those are important. And I remember, as I became a field applications engineer, part of our support we provide is training. And so I had to create slide sets to provide, operational training for our devices. And I remember my very first one, it was for a 68HC11, which was a very popular device in its day. It was taught in all the universities. I had like 200 transparencies, right? So that was when we had transparencies for the presentation. So I spent weeks putting together this presentation on my computer, and we were using, I think it was still PowerPoint back then, but then you've got to print the clear transparencies and then do the presentation. And it was really hard because I really didn't know the part that well, even though I had all these slides, and I had like probably 200 too many slides for a 2-hour presentation. And then so I made it through there. It wasn't very pretty. And it became evident the customers all knew way more about the part than I did, but they were very gracious. And that was from that I knew I needed to work on my skills in both creating the presentations and doing these presentations, and then just doing those over and over again, looking at how the customers respond to what you say, trying to listen to questions, and try to fine tune the information so that it meets the audience has been the goal all along. And then as I started to go to conferences to learn about EMC and signal integrity, I paid close attention to the way the presenters behaved and what they were doing. One comment though is when I first started going to all these classes, there were so many different perspectives. And every one of the instructors had the best intentions, but they would often say things were totally contradictory from one to the other. And especially when I was new trying to understand this, and this is something I want to make sure that the audience understands, that if something doesn't seem to make sense, then there are only two possibilities for that. One is that you don't really understand it well enough, which is good because that says, oh, I need to go study this particular piece of information. Or two, it's wrong. And you're going to find typically most of the time, it's not that you don't understand it, it's that it's wrong. And it was hard for me to be able to make that connection. So I would go into like PCB West is like 3-4 days of training and go to all the classes and just come back confused because it just couldn't understand who was right, how they could say this here and say that there, and why they were so different. And again, the intent is always a good one, but it's based on that particular person's experience. And if his experience was with TTL or HCMOS, rather than with the newer, special, faster parts that we have today, they're just talking what worked for them. And when I got to that point where I could understand that that was the perspective, then I could start putting some filter on what they were saying and look for the pieces of that discussion that were worth holding on to and knowing which things were just based on the rule that wasn't so bad it made it fail, not that the rule that was right. And started building from what I learned from Ralph, a list of rules that are based on the real behavior of electromagnetic fields and the rules that talk about how do you manage those fields correctly. And those are actually quite simple guidelines. And when you follow those rules, the result is success, EMC compliance, and signal integrity.
So what sort of team would require your expertise at NXP? And can you also mention some of the roles that involve expertise in signal integrity and EMC?
That's another great question. Once I learned about Ralph and Rick and the real science, I became very passionate about it and wanted to share it, especially within NXP now. And so I actually participate in various design teams. I'm asked to be part of the substrate design teams for our ball grid array devices. From that, I also work with the teams on even floor planning, where you put each of the pieces of the IC structure on the die, and how do we interconnect that to the PC board through the small PC board called a substrate. I also work with the teams that do evaluation boards to try to help to improve the behavior and quality of those boards. I work with the product test and burn-in teams. So I help them to improve the designs of the physical boards we use on our testers and the boards that we use for burning in the devices, and every chance I get. And then I also get called in by the field quality teams when they have found issues with customer designs. And then I will participate in design reviews with the customers to help support the effort to discover, why are they having an ESD event destroying devices? Is it a feature of the printed circuit board design, or is it something that they're doing to the devices during the manufacturing process where they're not controlling ESD in their factory? So quite a number of roles. I teach classes at every NXP internal event that I attend to try to share the approach, the in-field based approach with my peers within NXP as well. So mentoring within the company, and again, participating as an active member of design teams, in addition to my main job, which is the field applications engineer.
So Daniel, what made you start your career as applications engineer at FREESCALE Semiconductor? Two questions here. Why not other roles? And why did you choose FREESCALE Semiconductor to start with?
Well, I started out with Motorola, and I've been a technician in the Air Force and was looking for a way to continue my career in electronics because I enjoyed that quite a bit. And I started working as a contractor for Motorola in their microprocessor development tools group. I worked on 6800s and then eventually 68020 emulators. And I do not have an electrical engineering degree. I have the training certificate from the Air Force and the experience I gained there. And then I was fortunate enough to grow up within the microprocessor industry because it was just beginning in 1980 when I started working for Motorola. And through incredible mentors, patient engineers that I worked with, I continued to increase my role as first just a technician and then becoming an engineering assistant working on different types of devices, IC designs, and everything from fiber optic transceiver system, which was quite interesting. So I had a spool of fiber in my lab that was a kilometer long that we used to test our transceiver. And the cool thing was that the quality of the signal through that kilometer with our system when we developed it was better than through a 3-foot piece of coax. So that was pretty exciting. And then IC designs, but I was at the top of the pay scale and the top of the grades. I couldn't be promoted again unless I could find a way to become an engineer. And in 1986, Motorola just had an effort to increase the number of field application engineers that they had. And so they were offering this opportunity, and some of my coworkers that were engineers moved into field application positions. And I went to personnel and said, hey, I don't have a degree, I'm not an engineer, but I really would like to try for this because I've been doing engineering work for a number of years. And the response from them was quite positive. That if you can find somebody who will hire you in the field, then we'll make you an engineer. So that was my motivation to be a field engineer for what was Motorola. And then when we were spun off, becoming FREESCALE. And so the first year I interviewed, especially with one manager who basically said that I wasn't field engineering material. And so that was frustrating, but I didn't quit. And so the next time they had a call for engineers, I was able to find a manager, and basically he really wanted one of my coworkers but he didn't want to move from Phoenix because I was in Phoenix at the time. But he told him, he says, I'm not going to move, but you really want Dan. And so from that, I got an interview and was hired and became a field applications engineer, entry-level engineer. So now I could start my career over, having been maxed out as a technician to the highest level. Then I could start working my way through engineering, and now have made it to technical director, which is 6 or 7 levels above my entry level. And one of the really most exciting things is at one point in the, was it in the 90s? No, it would have been in 2000-ish, that there was a program where they were going to promote people to a senior level, a principal engineering level. And I was promoted to principal engineer before the manager who told me I couldn't be an engineer. So that was poetic justice to me, and continued my motivation as I worked more and more. So that was the evolution, and it's been fun. When I first came to work in the automotive team in Detroit, I at first expected to see a drop in the technology that I was experiencing, because I worked on the very highest end emulators for our most powerful processors when I was working in the design team in the factory. And I was so far from crew when I got to the field. In automotive, you're designed with technology that's 5 to 10 years ahead. So they're not using what's available today, and they're planning and they're working on what's going to be there when they're ready for production in 5 or 10 years. So I found that I was absolutely embedded in the highest levels of technology, and I didn't give up anything at all. And it actually was challenging me because I was working with technologies that were in advance of what I had been doing when I worked in the Motorola factory. So that's been great too. You know, it's a continuous learning event. The landscape is constantly changing. We're working on, 4 nanometer devices and high speeds that are in where you have 10, 20, 50, 100 gigahertz signals that you have to deal with. And that's where, if you're not following the rules based on the science, you have no hope of making things work. And the thing that Ralph taught me, though, is that the same rules apply no matter what energy you're using. If you're working on the fastest microprocessor in a network control system or high-powered AC transmission lines for electricity in your home, the rules are always the same. They just are ratiometric. If something's switching 10 times faster, then the structures you care about are 10 times smaller. And the only math you need is algebra. And the guidelines follow that, and it makes it so I can work on any kind of system in the entire electrical engineering world, because I know that the rules are always the same, and I just change the geometry of the structures that I'm using as they are driven by the switching speed of the transistors that we're dealing with. And it makes it so much fun and so much easier than it ever was before. And that's what I try to teach in my classes.
Great, great, great. And as Daniel, you were speaking about your career started into electronics just on the basis of training or on the basis of experience. But do you think having a formal degree in maybe electrical engineering or electronics would have given you an edge, or it doesn't actually matter over large scale of time? What do you think?
I think that in my case, I was in a unique time period in our industry. I think that it's absolutely necessary to get a degree at this point in most people's careers, because there isn't that learning curve that the industry is achieving. You're jumping into an industry that's mature and very much focused on the technologies that we have today. When I started working with these devices, they were so slow and nobody knew anything. And like I say, I wire wrapped a 68020 single board computer. It worked just fine. And I thought it was because I was a good technician. No, once I knew the truth, it was because the transistors were switching so slow that all of the components were within the lump distance. So there was nothing I could do wrong to make it not work, within reason. So I was following rules that were just not so bad they made it fail. Now you have to have that knowledge. What I would like to get the community to think about is that the circuit approach that's primarily the focus of the electrical engineering curriculum is going to kill you. And I've been working with as academics wherever I can to try to change the focus. And the article that I wrote, The $1 Billion Mistake, is to highlight why the circuit approach and the current in a loop perspective is the source of all of our evil that we have. And it's really important that you understand fields. And I know that most of the time it's presented in the universities. The fields classes are evil calculus and hard math, and there's been very little effort to connect the science of electromagnetic fields and their behavior to the electronics side. And that's where the disconnect comes. So what I would encourage all the students that hear this, and young engineers and senior engineers, is to focus on the energy. And that energy doesn't travel in a wire. It's the same energy in a radio signal as it is on a address and data bus on a circuit board. It's electromagnetic field, and it travels in a dielectric. So on the circuit board, you have to design waveguides for the energy to travel in, and that has absolutely nothing to do with current flowing in a wire. There is some charge movement, but the charge only moves because the field's pushing past it. And the field is bullying electrons in the outer shell of these conductors and making them move a bit. And that's the displacement current, but that's like the wake of the boat. The wake doesn't carry the boat. The boat is something different. It's like saying that the river banks are the current. No, the river banks direct the flow of the water. The two conductors that you use in a transmission line direct the flow of the energy. So you've got to be focused on the energy and the dielectric. And all you do is create the plumbing for that movement of field, and that's electronics. The rest of it has no meaning at all. It's a second order effect. And when I finally figured out that radio and signals on a board were the same thing, I felt really stupid, because it was like there was no magic that it changed from field in space to electrons flowing in a wire just because I put it on a circuit board. Because if circuit theory was true, there would not be any radio. You wouldn't have signal integrity problems. You wouldn't have problems with EMC. And we wouldn't be alive because the sunlight wouldn't get here. There's no wires connecting the sun to the earth. All of that is in front of us every day, that we still design circuit boards as if it was electrons flowing in wires. So please change your focus. If you want to be successful, the sooner you do that, the more successful you're going to be in your career, because you're going to be in great demand by companies who finally get it. And that's the problem, is the consumers of electrical engineering students, the companies that hire them, have not connected the dots. They get engineers who are trained in the current curriculum and are not successful in their design efforts because they design products that don't pass EMC. And it's because they aren't given the proper skill sets. And until the consumers of engineers go to the universities and say, we need you to change the skill set because it's not complete enough, they have no motivation to change the curriculum. In fact, Ralph Morrison went to Stanford and asked if he could teach a field-based class for them. And they said no, because they didn't want to change their curriculum. They don't want to spend the money because their product's being bought by everybody anyway. So that's another evolution that needs to occur, is the engineering community and the engineering companies need to be asking for a change in the curriculum. So the focus is on fields primarily, and then the secondary field focus can be on the circuit approach. But if you do circuits first and then fields next, the result is the engineers don't want to deal with fields, me included, and they like circuits because the math is simple. You know, it's RLC, I equal E over R. You know, that has nothing to do with energy flow. A resistor doesn't cause electrons to stop flowing. A resistor reacts with the field and converts a fixed amount of the electromagnetic field into kinetic energy. So it consumes some of the field, so that on one side of the resistor, there's a certain field volume, and on the other side of the resistor, that field volume has been reduced because it's been converted into heat. That isn't taught, but that's the reality of our world. So learn about fields. It will be very powerful in your career.
Cool. So that is something that our young engineers need to take into consideration along with the universities. So yeah, that's one take that the viewers can take from this podcast. But other than that, fast forwarding, what does it take to become a technical director? And also, what does it take to become a senior IEEE member?
That was an exciting adventure. It's beyond your ability to perform. Your knowledge and your experience are important. I had to have, you know, a large amount of experience as an engineer. For technical director and for the IEEE senior member promotions, which I've been so fortunate to get this year, it's your impact on the industry and your peers that really becomes important. And, you know, certainly within the technical community, they want to see patents. I don't have any patents of my own. I've worked on a number of patent applications with team members within the NXP. But it's what impact have you had on the industry? And I've been teaching classes on EMC and signal integrity for more than 10 years now. I'm an invited speaker at conferences worldwide. I work with customers on a global basis with great success. Once I present the field rules and they start to change their designs. And so I've had a pretty big influence, I think, on the world of engineers. I've taught several hundred classes over the years to over 10,000 engineers. And it's, you know, that is the level of impact that they're looking for on what I've had to change the world and continue to try to do so. So that's the outside impact is what really makes the difference when it comes to those two types of designations.
Great, great. So Daniel, we would be moving to the end of this podcast. But before that, is there any motivation that you want to give to young electronic students, be it career or life advice? Before that, please also tell what drives you, even after having spent around 40 years in the industry, to continue.
Well, my suggestion again would be to pay attention to the science and to question things. If it doesn't make sense, most of the time, it's because it's not true. And I know, especially as a junior engineer or a newbie to fields, when you want to present the concept of fields to people who are not well versed or don't believe in it, it's difficult. It's daunting because they want to argue with you. And if you're not confident in your knowledge of the science, then it's difficult to present an argument that will hold against, we've done it this way for the last 20 years. You're new. We don't have to listen to you. And the sad thing is they say that in spite of the fact that their design just failed using their guidelines. And I face that a lot with my customers and within my NXP community, that their experience tells them that this is how they want to do it, in spite of the fact that what they did just didn't work. And there's not a connection of what did I do wrong, you know, what in my methodology was wrong, you know, and they keep just doing the same thing over, but just a little bit differently. And that whole, it's not engineering. That's, you know, wishing and hoping. Engineering is if you build something, you test it, something doesn't behave the way you want it to do, you analyze that to see what it is that needs to be changed. You don't just ignore the fact that it didn't do what you told. You don't do the same thing over again and hope that it works this time. And that's the thing that I find is happening still in the industry. I have customers, big customers, billion-dollar companies that admit that it may be 3, 4, or 5 respins on their circuit boards before they finally become compliant. That's a lot of wasted money and design effort to finally get to the place they should have been in the beginning. And instead of looking for root cause, they look for which wire do we move, or which silicon vendor do we blame? And that's not engineering. No, and engineering is a disciplined approach. And this is what I've been lucky enough to learn to a problem. You analyze it, and then you make changes based on the results of your analysis, looking for ways to improve the methods that you use to design that. And then I see some other topics you wanted to talk about as far as my interaction with the Indian engineering community. So if you want to introduce those, I'd like to address those as well.
Yeah, we will do that for sure. But otherwise that, it was an incredible episode so far. And thank you once again for sparing time for this. It was pleasure talking to you.
I say I've been fortunate enough to work with a number of engineers from India. NXP has several design centers. I've been to Bengaluru several times with the FREESCALE technology forums where I was teaching my classes and was able to meet hundreds of Indian engineers at the time. My patent applications that I've been involved with were with my peers in India in our design centers there. So that's always good. I love Indian food, which makes it even better. And I just found that about the India PCB, or PCB India, which I am joining today. I'm a member of PCB Africa as well. So the idea is that especially I've worked with Indian customers on high-tech designs, automotive and embedded computer systems. And I see that the efforts by the Indian government and Indian companies to build new fabrication plants and continue to improve the expertise of the engineering community in India are I think they're well thought of and moving in the right direction. And I feel this is a great time for me to be able to mentor that community as well. So yeah, I think there's a lot of excitement and promise in what's happening in India today.
That's great. That's again a plus point for us for knowing some perspective from outside. And yes, I hope that India will also be on top in electronic system one day.
Yep, I hope to visit again sometime soon.
Yeah, sure. Yeah, anyways, sir, it was again pleasure talking to you, and have a great day ahead.
Okay, thank you very much. And we'll be speaking again soon, I think. Thank you.